Functional dependency in DBMS. What do we mean by functional dependencies and how it gets reflected in relational database management system? Hello everyone, I'm Sukanya from Additive Technologies, and in this video we are going to discuss about functional dependencies in DBMS. So the very basic definition is that functional dependency is a relationship between two attributes, that is between the primary key attribute and a non-key attribute within a particular table. For example, this relationship X and Y. So it is a relationship between any primary key attribute and any non-key attribute. The left side of functional dependency is known as determinant and the right side is known as the production of its dependent. So this is known as determinant X side and the Y side is actually known as the production side of that particular dependent. Now another definition of functional dependency could be alpha belongs to beta holds if two tuple having same value of attribute alpha also the same value of attribute beta. If alpha and beta are two sets of attribute in a relational table R where alpha is subset and belongs to R and beta similarly is of that particular relation table R, then the functional dependency could exist in this following form and it can be represented in this particular table. Similarly, the functional dependency FD is alpha, which is the determinant, and B, which is the production, beta, which is the production rule. Now, there are types of functional dependency. The very first type of functional dependency is trivial function dependency. Now, trivial function dependency comes with another form, that is non-trivial dependency. These are the two types of functional dependency in the DBMS. Now, to begin with, trivial function dependency. A functional dependency X to Y is said to be trivial if only Y is subset and belongs to X. Thus, if RHS of a functional dependency is a subset of LHS, then it is called as a trivial function dependency. So these are the two characteristics how a trivial function dependency could be said. If the functional dependency is said to be trivial if Y is a subset of X and also if the RHS of functional dependency is a subset of LHS, then it is known as a trivial function dependency. Similarly, here are a few examples of trivial functional dependency, which as AB, every element of A belongs to AB, which means AB is actually the determinant and A is the production rule of it. Similarly, every element of B is found in AB and every element of AB is obviously in AB. Now next is non-trivial functional dependency. Now what is a non-trivial functional dependency and how it is different from trivial function dependency? So a functional dependency X to Y is said to be non-trivial if and only if Y is not a subset of X. That means elements doesn't belong to the set of X. Thus, if there exists at least one attribute in the RHS of functional dependency that is not the part of LHS, then it is called a non-trivial functional dependency. Here are a few examples of it, that is every element of B and C gets into the set of AB and similarly for CD. Now there are several inference rules for calculating the different dependencies and those are, first is reflexibility. If B is a subset of A, then A belongs to B always holds. Similarly, transitivity, which we have already studied in our very primary classes, that if A belongs to B, that is in every element of B there is A, and similarly B gets to C, then A is for C always holds. They have the common elements. Next is augmentation. Augmentation, if A gets to B, then AC always holds to BC, where C is a common set, so it can hold in both. Similarly, for decomposition, if A gets to BC, then A gets to B and A gets to C also. Decomposition means we differentiate the attributes, we decompose the attributes into single set. Similarly, composition is the combination. If A gets to B, then C gets to D, then AC combiningly gets to BD, which always holds true. Similarly, there is additive property also. If A belongs to B and then A is also the C elements is also in the set of A, then it is always true that A gets to BC. The decomposition is exact opposite of the additive property. In decomposition, we get into single sets, and in additive, we combine the respective sets with respect to the determinant and the production rule. Similarly, there are several rules for functional dependency also. The rule first is a functional dependency X to Y will always hold if the values of X are unique and different irrespective to the values of Y. So, functional dependency will always hold if the value of X are unique and irrespective to the values of Y, then it will always hold true. So if you consider this following table which is shown here in the example, then how can you see that the following functional dependency exists? That is, A gets to B. The following functional dependency will always hold since all the values of attribute A are unique. These values are unique of all the attributes. So A is always the determinant set, and these are the production rule. That is, A gets to BC, A gets to B, C, D, B, C, D, D, E, and B, C, D, E. So these are all the functional dependency. They are the dependent attributes. So in general, we can say that the following dependency will always hold true. That is, A is any combination of attribute of A, B, C, D, E, which is true. Any combination attribute of A, B, C, D, E gets to A. Similarly, will the case of attributes for B and E also, that any combination of such attributes gets to B and E also. The rule 2 of functional dependency is, if a functional dependency x to y will always hold if all the values of I are set respective to the values of x. If the values of y are irrespective to the values of x, which is exact opposite of the rule 1, then also we can say that functional dependency exists, and the combination will have a reverse order. That is, any combination of attributes A, B, C, D, E will gets to C, because C has always the same set of values. Here you can see that C set is always having the same set of values. So any combination will definitely have C, any combination of A, B, C, D and E. So combining both the rules, in general what we can say that a functional dependency alpha to beta always holds if either all the values of alpha are unique, or if all values of beta are same, or both. If both the values are unique, if one value is same, or both the set of values are same, then the functional dependency alpha to beta will always hold. Similarly, there are two other rules also. Those are, for any functional dependency x to y to hold if two tuples are in table agree on the value of attribute. That means they must hold and also agree on the value of any particular attribute of y. Another rule is, for the example or the functional dependency such as x belong to y, violation will occur only when two or more same values of y, the corresponding y values are different. If the values are different, then obviously functional dependency doesn't hold. So in DBMS, two different set of functional dependency for a given relation may or may not be equivalent. It is not necessary that the functional dependency has to be equivalent. For example, if f and g are two sets of functional dependencies, then following three cases are possible. Now what are those three cases? Let us study that. Equivalence of two set of functional dependency, and how can we make them equivalent? So the case one is f covers g. This is the symbol. F is the cover of g. Next case is g covers f, and both cover each other. That means both the sets are equal. The values are same in both the sets f and g. So determination of, how can we determine whether f covers g? So the step 1 is, take the functional dependency of the set g into consideration. Then for each functional dependency x belongs to y, find the closure of x using the functional dependency set of g. The step second is, take the functional dependencies of the set g into consideration. For each functional dependency of x to y, find the closure of y using the functional dependencies of set f. In the last step, what you have to do is compare the result of both the sets. If the functional dependency set of S has determined all those attributes that were determined by the set of G, that means F covers G. Otherwise, we can conclude that it is of some other case, or else we conclude that F covers G and we have to use this particular determination symbol, otherwise not. Similarly, for determining whether G covers F or not. So the very first step is, take the functional dependencies of set F into consideration. For each functional dependency of x to y, find the closure of x using the functional dependencies of set F. Similarly, take the functional dependencies of set F into the consideration. For each functional dependencies of x to y, find the closure of x now, so that we can say that the functional dependencies of set G exist. You have to compare both the result, and if you find that G is the larger set which is the subset of having F, that means G cover F. And when both the covers are equal, that means F also covers G, and similarly G covers F. That means both the set covers are equal and both the elements in the set are equal. Thus we can say that the case 3 holds true, and we conclude that both the F and G cover each other, which means F is equals to G. So this is how we can calculate the set or the equivalent set of two any functional dependencies. In this video, we have studied about what are functional dependencies, what are the inference rule, what are the two types of functional dependencies, that is trivial and non-trivial, and then how can we calculate or how can we check that either there any holds equivalence of two sets in the functional dependencies or not, and their respective cases. For next videos of functional dependency and the examples, we will look into other videos. Thank you.